I would like to invite our distinguished guest, Mr. Bill Gerstenmaier, and whosoever came late into this event. He is the Associate Administrator for the Human Exploration and Operations Mission Directorate at NASA. And he is going to talk about or update about the NASA's plan for exploration of deep space. And the seminar is titled Orchestrating the Movement of Humans into Deep Space. So let us welcome Mr. Gerstenmaier with a big hand, please.
Down button is next. There we go. And okay. Did you want a wireless mic?
I guess I could do it here.
Okay.
Well, first of all, we ought to really thank the students for what they just presented to us. They've done a tremendous amount of work over 2 semesters looking at a whole variety of the challenges associated with Mars. And if you look at the challenge of Mars, I think when you look at the data that they presented to you, the charts they presented to you, you get a concept of how big a challenge this is. And even the questions from the audience were really rich. You know, many of these topic areas could be a semester, could be a year, could be several months of work in these individual areas. But yet the students did a tremendous job of integrating this all into a coherent plan of an activity that shows that this is really technically feasible. There wasn't any real magic in any of the hardware, just a lot of hard work, a lot of effort that goes in that puts all this stuff together. So what they showed you is possible, and it's a sense of what's real. It also shows us another reason for doing this is it also helps us here terrestrially. You know, these problems that are forced by going to Mars of how you keep humans alive for an extended period of time and how you grow food and how do you recycle water and how do you keep supplies and logistics, how do you take care of the environment that you live in. All those problems that we're trying to solve for Mars have direct application back here on Earth. So how we can do better food production, how we can look at revitalizing the atmosphere, how we can do in situ resource utilization, how can we better use resources on the Earth. So this challenge of Mars actually pushes us as a species to learn more about things that can actually help us to live better here on the Earth. So I think that's another dimension that was pretty clear from the presentation from the students. So what I'll do now is I'll talk to you just a little bit about, fairly shortly, what NASA is doing and what we're moving forward. And you saw a little bit of it in the students' presentation, the activities at the very beginning. We have a lot of hardware and work today throughout the country. We have a crew on board Space Station. A crew of 5 is flying on station today. They've been there for 16 years. So we're really actually living the first part of this vision that the students showed you. And so I'll show you some concepts. I'll show you some things that we're thinking about in terms of next steps, future pieces, and also try to tie those to the real activities we're doing moving forward. So I call this Orchestrating the Movement of Humans into Deep Space. And I chose those words pretty carefully. I chose the word orchestrating because I think the idea of NASA managing and doing all this activity on their own, of a single country, of having the finances and resources to do an activity of this magnitude is just not very feasible, is not practical. So I see our role as more of an orchestrator where we take the best and brightest throughout the world, throughout the international community, throughout the private sector, throughout the academia community, throughout students. It takes all of us to come together. So if we can provide a basic framework that can change over time, a basic resilient architecture, key pieces of infrastructure NASA will help go do and facilitate, but then that'll be augmented by the private sector, by other international partners, by students, by citizens in general. So this is a plan to actually move human presence in the solar system. As Shrag said earlier, why we want to do that can be debated, but as we do that, we need to do that in a different way and not as a single monolithic one type of project or one type of program. So our goal is the nation's goal for space exploration is to lead an effort that expands human presence deeper into the solar system through a sustainable human and robotic space program. And that's just simple terms of what we're trying to do at NASA, and we're trying to do that through this orchestration role that I just described to you. We have some principles that we've been using as we put this together. These are very high-level principles, but we wanted to build essentially just a basic concept that we could all kind of use, and they're more the kind of how we might do this. So the terms are here are fiscal realism. First of all, we don't think we're going to get a huge new increase in discretionary budget. We're not going to get a brand new influx of money to go do a major program. NASA's been pretty stable as about roughly 1 to maybe 0.5% of the gross domestic product in the U.S. We think that's where we're going to stay. We'd like to build plans that are commensurate with economic growth, maybe 2.5%, 3% growth per year, but that just keeps us even, and then that requires us to build and leverage off of the private sector, leverage off of international involvement to keep these activities moving forward. We talk about scientific exploration. What that is the robotic spacecraft really inform us of what we can do and how this comes together. So it's a shared activity between the Science Mission Directorate and Human Exploration Directorate. Today there's a rover on Mars, actually has a radiation detector that monitors the radiation environment on Mars. So we don't have to speculate about what a solar particle event looks like on Mars. We have actual data from Mars on what a solar particle event looks like. We can also see the diurnal variation in radiation from day to night on Mars as the atmosphere expands. And I think the radiation environment should be looked at pretty carefully in terms of what we've seen from the RAD instrument on board the Curiosity rover. I'm not sure it's as bad or as demanding as some of our earlier studies had thought when you actually look at the data. The free space transit is a very demanding environment from a radiation standpoint, but the atmosphere of Mars, even though it's fairly thin, does a fairly decent job of removing a significant amount of the radiation that comes from the sun. Technology of pull and push. What we're trying to do is infuse technology into our program where it makes sense, but don't put brand new technology in the critical path of a new activity that helps us moving forward, but also build a plan that allows us to interject and bring new technology in where it makes sense. We gradually build up capability. The near mission goals and opportunities, they appear on a cadence of compelling and integrated mission timelines, but we also build off of the previous components and use them in the future. So we don't build single systems for one activity. We build a system that we can use multiple times for multiple applications. So as you saw from the students, some of the lander technologies, those need to be common. As we build a solar array system or a solar array design, that design needs to be carried into other designs. It's not a single one-off design. We're essentially building a series of systems that can be used together to continue to move us forward, and that's the gradual buildup of capability. We're looking for economic opportunity. We're trying to get the private sector very involved in low Earth orbit, where they might use the space station as a springboard to learn how to actually generate revenue from space activities. We're starting to see some interest from the pharmaceutical company for the first time. We're starting to see some manufacturing interest for the first time. And what's interesting is the private sector is now looking at revenue generation from activities in low Earth orbit. If we can create an economy where the private sector is interested in research in space and can generate revenue from that activity, that builds a broader base for us to move forward. We want to have an architecture that's open and resilient. So we want to have an architecture that doesn't lock us into one path. If a new technology comes online, a new partner wants to come and participate, or new technology comes online, we can interject that into the architecture and move forward. We see this as a global activity. I think you've heard that from the students. I think we all see this as this can't be done by a single nation. It needs to be done as a collaborative activity. And then the last piece is I believe strongly in the continuity of human spaceflight. We should not end our activity on the International Space Station, for example, until we've begun a significant activity beyond low Earth orbit, working in either lunar velocity or heading towards Mars with humans in space. I think it's important we have a continuous cadence of taking humans into space. And this is the basic principles that NASA is trying to use to put together our plans and architectures as we move forward. This is the way we've been talking about it. We break it out into phases. You could see here phase 0. That's where we are on Space Station today. We're using Space Station to solve exploration mission challenges through research and systems testing on the ISS. We've dedicated 4 racks on board the space station to be the next generation of life support systems that will be used for exploration class spacecraft. Today on space station, we have the water loop closed at about 86%. We believe we can close that water loop to 93%. We will do that, demonstrate that on station. We'll also develop the high reliability systems needed for these Mars class missions on station. And then we'll understand, we also want to, during this phase 0, we also want to understand if and when lunar resources are available. So we know there's potentially water on the moon, and if that water is available as a propellant source, we think that's a really important thing in terms of the architecture going forward. So we want to do, during this early phase, this phase, which is essentially now in the next several years, to get some kind of resource prospector on the surface of the moon to understand how those water resources are held in the lunar regolith. And then the last point is also really important, is we want to develop some standards. We want to have some standards out for all countries can build to. We want to set the atmospheric standard for the pressure inside all the modules of the space elements. We think that should be 14.7 based on where we are today. And even though that causes you to carry a little bit performance penalty in terms of pressure shell and other things, we think the physiological and the human research we've done all at 14.7 is really important to keep that pressure. We have partial pressure of carbon dioxide limits we'd like to set. We have power bus limits we'd like to set, some data bus limits we'd like to set. We also already have an international docking standard that's published on the web. It doesn't tell you how to design or build the docking standard, but if you build to the docking standard, you have docking compatibility with any of the vehicles that are coming on the United States side. So if we can build those standards, then anyone can build to those standards, then we can take their hardware and interject them into the architecture as we move forward. The next phase we see is phase 1, where we conduct missions in cislunar space, and we assemble a deep space gateway. I'll show you what that looks like in the next couple frames. And then I'll talk to you about a deep space transport, which is essentially our vehicle that we'll use to go beyond the Earth-Moon system. In phase 2, we complete the deep space transport and we conduct a Mars verification mission. Maybe in 2029 is our plan, so we actually simulate what it would be like to take this vehicle on a journey to Mars, and do a 1-year verification mission to verify that the system hardware is ready to go. And then the goal is by 2033 to be on an orbital mission to Mars. At the same time, we have phases 3 and 4 where we're working on the entry, descent, and landing activities. We recognize there's a lot of development activities. As the students showed you in their presentation, we see the same problem with the entry, descent, and landing problem. How can we get data on that activity? We're very lucky in the fact that SpaceX would like to go fly a Red Dragon capsule or fly their Dragon capsule to Mars in roughly the 2020 timeframe. NASA will participate with them and help them with that activity, providing deep space network coverage and navigation support for them. In exchange for that work, we get entry, descent, and landing data, supersonic and hypersonic retropropulsion data into Mars from the Dragon capsule. And that's a great cooperation between NASA and the private sector, where they have an interest in doing something. We have facilities and resources. We contribute that to them, and we get data back, which helps us understand entry, descent, and landing. This is, you saw the clip in the student's presentation on the NASA Authorization Act. This is the act that was signed by Congress and the President. It's pretty exciting to me if you read the words here, and I won't read them to you. The long-term goals of, I'll read some of them to you. The long-term goals of human spaceflight and exploration efforts of NASA shall be to expand permanent human presence beyond low Earth orbit, and to do so where practical in a manner involving international academic and industry partners. And if you read through this Authorization Act, this is exactly what we've been talking about doing. This is exactly consistent with the goal that I showed you on the very first page. So for first time, we really have strong congressional and administration support to an agreed to set of goals for the activities we're about ready to go forward on. And I think that's a big step, is to have this general agreement of what we're trying to do moving forward, rather than a debate about small destinations or other pieces. That also breaks down on the next page into key objectives, and you can see those objectives. Again, I won't read these to you. You can take a look at them in the actual act itself. But again, they're 100% consistent with the items I'm going to show you coming up, and they're consistent with our general plan of moving human presence into the solar system. If you take a look at it, how we're going to do this, we're going to do this by maximizing utilization of the International Space Station. We think that's a unique asset, both from a technology standpoint. It can also help the private sector gain experience in learning how to generate revenue in deep space. 14% of our global launch market goes to the space station today. So 14% of all launches that occur off of the Earth today are going to space station. Space Station was able to provide the cargo services contract to Orbital and SpaceX, which allowed them to essentially create a new market to lower launch costs, which will be a tremendous advantage to us. So that's wasn't really in the original purpose of Space Station, but it's a tremendous capability we got from Space Station. So we need to really look at creative ways of using this unique asset. It's also set up very strong intergovernmental and memorandum of agreement or understandings with many countries, with the 4 partners. There's been 86 countries have flown research on board the space station. We can use Space Station as a model for international cooperation. We're going to actively promote low Earth orbit commercialization, as I described. We need to create an economy where the private sector can generate revenue in low Earth orbit. That augments NASA's budget. That's funding that can come from the private sector and doesn't require government funding. We're going to resolve the human health and performance challenges. We see the human and performance challenges associated with Mars as broken down into 33 major items, and we're working through Space Station and through ground research to essentially retire the risk of those 33 items. We're growing international partners. We're building on the critical deep space infrastructure, and I'll show you some of that on some of the next charts. And we're enabling capabilities to explore for multiple destinations. So it's not a single focused mission to one destination. It's not a single focus to one region. It's essentially a basic infrastructure which needs public-private partnership involvement, needs international involvement to make it a whole program to essentially move human presence into the solar system. So we talk about this in phases. This is the Orion capsule over here. That's in manufacturing for Exploration Mission 1. It's in Florida today. The structure is there. It's undergoing internal outfitting. The service module is in Bremen, Germany, being manufactured. In completion, it should be ready to fly in 2019 in an uncrewed version, and that vehicle is moving forward well. This is a concept of what we think the Deep Space Gateway will be like. We know the basic volume, we know the basic power, we know the basic capabilities of it, but the concept and the actual modules and how it actually comes together will be defined over the next several years. This first piece here is a solar electric propulsion bus. It's a hybrid bus. It has some chemical capability as well as electric propulsion. It was part of the asteroid redirect mission activity. That piece of infrastructure we have the contracts, we have bids for those, and we're going to go evaluate those and determine where that fits in our overall architecture, but it's essentially ready to go into contract and get procured. We see this is a 40 kilowatt end-of-life solar array system. It has 12.5 kilowatt thrusters on the back, and it has 4 of those thrusters available. And we see this system as being extensible to the higher power solar systems that are needed for later for the Mars class missions. The basic functionality is up here. The Deep Space Gateway provides the ability to support multiple U.S. Commercial and international partner objectives in this phase 1 that I showed you on the first page. It supports Dr. Orion with crew of 4 up to 42 days, so it's crew tended. It supports buildup of the deep space transport. It provides a destination to build the vehicle that will go beyond the Earth-Moon system. And there's an open trade of whether we want to take this into low lunar orbit. This vehicle can be maneuvered around the moon. It can be in a lunar polar orbit. It can be a lunar equatorial orbit. It can be in a distant retrograde orbit. It can be in halo orbits around L1 and L2. This is a very flexible destination or temporary space station. It can be moved to these locations to do scientific investigations from any one of those regions. So we see it being able to drive rovers on the surface of the moon to do other activities along those lines. We're putting a lot of emphasis today on these pieces, the power propulsion bus, the habitat, and the logistics strategy. We have some work to do on the airlock and the future deep space transport. So if we take a look at how that comes together, we see again the first flight of SLS in roughly 2019. That's without a crew presently. We've been asked to go look at putting crew on that flight, and we're currently in the process of investigating that. We also have a request to go look at using Europa Clipper to take a mission to Europa for the Science Mission Directorate. The advantage of SLS is the lift capability, or the C3 capability of SLS allows us to go to Europa Clipper without a Venus flyby and a Venus assist. So it cuts the transit time to Europa. It cuts the transit time to Europa without a Venus assist by about 3.5 years. So you can be in the vicinity of Europa instead of 7 years in about 3.5 years. The launch window for this mission is about every 13 months. I don't know whether it will fly before the first crewed mission of SLS and Orion or after. I think more than likely we'll probably have the crew mission in 2022, and then we'll follow it with the Europa Clipper mission in 2023. And you can see here it's still subject to approval. We still need to get some reviews through some of the political channels in Washington. But again, this is a concept we've been asked to go look at, and we're working on that activity. Down here on the chart, you can see what we carry with us on each one of these Orion SLS flights. So on this first Orion SLS flight, we believe we can carry that per power propulsion bus. We could do that as early as 2022. We put that in cislunar space. Then on the next flight, we can carry along with Orion a habitation module. The crew can go into the habitation module and actually do the activation of that, so it doesn't need to be done robotically. The habitation module attaches to the power propulsion bus. We can now maneuver that in the vicinity of the moon, anywhere we'd like to go do subsequent missions. The third mission, we bring up logistics that allows us to extend the crew duration out to 42 days. And we also bring up a robotic arm on the outside. And then we see another flight potentially to bring up an airlock. So essentially in 3 flights, EM2, 3, and 4, over 3 years, we can have a capability in cislunar space to do the first steps of moving human presence in the solar system and be in a way to do things moving forward. What's also good is all this activity is underway, as I described to you. This power propulsion bus is actively being worked on. The contracts or the proposals have been received. We'll determine what we want to do with those. This habitation module can come either from the private sector in the U.S. through the Next Step BAA activity we have, or it can come from international partner involvement. So that activity is moving forward. Logistics needs a little bit more work and definition and findings. But again, all this fits within the basic budget profile we have, which we call our current services budget, which increases at about 2.5% per year. It doesn't, and this can operate at the same time we're doing space station activities and other things. So this is the beginning of how we begin this process. On the next chart is the next piece, which is the deep space transport. Again, this is similar to what the students showed you. It has the proper volume, it has the right logistics. Again, it has electric propulsion augmented by chemical propulsion. It's the vehicle that goes beyond the Earth-Moon system. This probably isn't the way it's going to look, but it's of this concept, this size. Again, the thrusters would be of the same next generation of electric propulsion thrusters, so from instead of 12.5 kilowatts, maybe up to 25 to 30 kilowatts of power for the thrusters, and the solar arrays will be substantially larger in terms of hundreds of megawatts of end-of-life power. So this is what that looks like as we flow that on out a little bit. You notice I changed the nomenclature here. I call this planning reference. This is not as firm as the previous chart you saw for the phase 1 and phase 2. This still needs some work. The idea here was to do the deep space transport as one piece, to launch it as a single monolithic piece without any logistics, without any propellant, and that's roughly a 41 metric ton capability. And we think that fits with our overall capability. Then we use multiple logistics flights. We bring up a substantial amount of refueling and propellant systems and more logistics, All of that to get really ready for this 1-year verification mission to check out systems to make sure things are really ready to operate. And then in the 2030s, we again then outfit it again. This deep space transport is designed to be used multiple times. It's not going to fly to Mars, the vicinity of Mars, just once. It's designed to fly at least 3 times and be refurbished in deep space, plus the 1 flight for the checkout. And so you can see over here on the side, we start to describe where we've nailed some of the parameters, some of the requirements are understood. These are some of the more open areas that we've still got to go do and work as we go forward. So we've taken the task of a big task and we've broken it down into things we need to decide now, things we can decide a little bit later, actively trade back and forth, see what new technology comes online, see which partners are available, see what interest is available from the private sector, and fold that into this plan. And that's the effective way that we're orchestrating what I just described to you. And again, this is the basic functionality. I think I described all this to you, the 3 flights, 4 crew for 1,000-day missions in deep space. It doesn't have to go to Mars. And what's missing from this, obviously, is the Mars landing activity, which we need to be working on parallel out in the 27s. We'll do this shakedown or verification cruise in 2029. And then we're still training the actual details of that cruise. Does it stay in the vicinity of the moon? Does it go other places? And then we need to work on the Mars reference mission fundamental requirements. So this is the basic plan. And again, today you can see physical hardware for all of this stuff. You can go to Germany. You can see the actual service module we used on Exploration Mission 1. You can go to the Kennedy Space Center, see the actual Orion capsule that's being manufactured. You can go to New Orleans, outside New Orleans at the Michoud Assembly Facility. You can see the hydrogen external. We have two hydrogen external tanks down there, an engine section structural test article. The oxygen tank is being manufactured now. The propulsion systems for this have been tested extensively at Stennis. The shuttle main engines are the propulsion system for this device. They've been operated, they've been fully qualified and are ready to go. We're flying a new flight controllers for those engines. They're fully checked out. We had the first 4 missions of engines available to us already, all ready to go fly. The solid rocket boosters have been always fully qualified in Utah. We've done 2 qualification firings that have those human rated and ready to go fly. We're pouring the segments for Exploration Mission 1, and we're beginning to start doing the layup of the castings for Exploration Mission 2 on the solid rocket motors. So this is a real program with lots of development going on every day. At the same time, in parallel with that, we have our 5 crew on board space station. We're working actively with SpaceX and with Boeing to build the crew transportation systems for ISS. So I think it's a really exciting time in human spaceflight. It's exciting to see what the students presented to us here earlier. They show a vision of the future out through 2100, which is an amazing time, but they show the ability to put 50 people on the surface of Mars, which is amazing. And then today I show you the simple first steps of how we're actually going to start to deliver that vision that the students talked about earlier. So thank you very much.
So we'll take questions now. So Pablo, if you can help us. Thank you.
This may be a difficult question, but we talk about American leadership and so on, and my question is, how independent are we prepared to be if we have, for example, China and Russia and so on, and we have ground disputes and we're planning long-term missions that are decades long? To what extent are we prepared to go it alone, in the sense that some service or component may not arrive that we need? Has that issue been wrestled with a lot?
We wrestle with that issue a lot. It's much like a corporation. When they decide to, do they build something in-house or do they go acquire it out from another vendor? Where do you put a partner in the critical path? There's a lot of folks that would like to have no one in the critical path. They'd like us to lead everything. Today, honestly, we're dependent upon the Russians. They provide transportation for us to and from space station. They are in the critical path for our activities. We also have consciously put the Europeans in the critical path for the service module for Orion. We did those things smartly. In the case of the service module with Orion, we have the intellectual property, so if we chose in the future to go build that in-house, we have all the design information that we could go build that in-house. I think our preference is to do it with an international partner, and we chose to put them in the critical path for the first flights. We think that, and that was only done because of their support to their space station. They've proven to be a reliable partner. In the case of Russia, it's not often known or discussed. The Russians are also very dependent upon us. We provide all the power for the Russian segment. We process about 1,000 to 2,000 commands, go to the International Space Station destined for the Russian segment through U.S. assets. So we are very much intertwined and dependent upon each other. I think in the future, we're going to have to be dependent on each other. I don't think we can carry the burden of being totally independent. We need to accept that and then figure out a way that we can mitigate it if strife or turmoil comes online. It's a very precarious situation in a sense now with Russia. We have a lot of political tension between the two countries. So far, the governments have chosen to leave space out of that discussion and debate. I don't know that that'll continue. We need to be prepared in case it doesn't. But so far, it's worked well, and I think that's an example that space has a higher calling for us that helps us overlook some of the terrestrial differences we have, some of the political differences we have, and I think that's another benefit of space flight. So I see that as a concern, but not as a problem. It's something you need to be aware of, make conscious decisions, and move forward in the right way. And we've done that. It's not comfortable. I get beat up all the time. Why are we dependent upon the Russians? Then it's funny, I go to Russia, and I'll meet with my Russian friends, and they'll go, "You've ruined us. You're buying transportation from us. We can't develop a new vehicle. You're building essentially 3 vehicles, a CST-100. You're building a Dragon. You're building an Orion, and we're still, flying Soyuzes for you. You've held back our space program. You've ruined our space program." That's what the Russians tell me. In the U.S., they tell me I'm dependent upon the Russians. We haven't launched anybody from the U.S. We have no space program. So I've determined that both sides, we tend to focus on the negative and explore the negative. But if you switch it around, it's maybe not so bad. But you just have to live with that natural tension. That was a long answer, but I wanted you to hear that there's thinking behind all that.
Is this Deep Space Gateway going to be able to service the James Webb Space Telescope at L2?
We'd have to go look at, when we could look at the xenon load, we could potentially slowly get out there. I don't think it would service in a sense, but it could be maybe in the vicinity. The problem with James Webb Telescope is it's a fairly fragile instrument. It has those the huge mylar radiator thing, and it's going to be very difficult to get in with any kind of spacecraft and not do significant damage to James Webb as we go. But I could ask some of my NASA friends who, as we're starting to size what delta V capability, we're finding out with electric propulsion and a lot of time you can go a lot of different places, and that's a very unique way of doing business. So we'd have to go look at the specifics, but potentially.
Yes, is there any real work being done on a space elevator, or is it just more or less hyperball there?
There's some studies and academic papers being done on space elevators. I'm not familiar enough to talk intelligently about what's being done.
Bryony Horgan. I'm part of our growing planetary science group here at Purdue, and I'm curious about how robotic exploration plays into this plan. Because on the SMD side, we've heard a lot about, that's the future of the Mars program. But right now, as far as I can see it, the Mars program has no funded future beyond the Mars 2020 rover. And so I'm curious what your thoughts are and how you see robotic exploration playing a role in this path forward.
Yeah, we're starting to work a lot with the science mission director to start thinking about joint missions. How do we learn more about Mars? The only reason we can talk about Mars the way we do is because of all the robotic spacecraft that have been there. We get, like I said, we get the radiation. I can get daily radiation measurements from Mars. I can get temperature and wind measurements from Mars. I can actually get weather reports from Mars today, which is pretty cool. And that's thanks to the robotics folks that are there ahead of us. The fact that we know where water is, that the students showed, We know that because of the robotics program. They're very interested in doing a sample return activity. As they think about that sample return activity, there's a natural chance to maybe test out some lander technology for us. This Red Dragon thing I talked to you about, where SpaceX is interested in landing on Mars, we'll learn about that. So I think you're going to start seeing science and human exploration get closer together to start defining joint objectives. Same with the moon. We're interested in understanding the volatiles on the moon for propellant use. I think the science mission director also may have some interest in lunar activities as well. So I think you'll see more and more closer activities. On the next 2020 Mars rover, right, there's a device called MOXIE. It's another thing that wasn't discussed by the students, but it has the ability to pull oxygen out of the Martian atmosphere, out of the CO2 atmosphere. That's another potential source of oxygen off of Mars. So it's not just the water on Mars. You can also use that carbon dioxide atmosphere as a nice resource to be used for lots of things.
Wonderful presentation. My question is on where do you see the commercial or the private sector role in supporting NASA's developing all this infrastructure, supporting the space infrastructure, the Gateway spacecraft that you have there. Is this something that you hope would happen, or is this kind of something that you would push for the private sector to take a leading role in?
We see it as required, and I didn't call it out on the chart specifically, but you can see here all these cislunar support flights are shown down here. So SLS flies maybe once per year, but then it's augmented by SpaceX, and it's augmented by ULA, it's augmented by Orbital ATK. Whichever rocket systems are there, they can take 1 to 2 metric tons to the vicinity of the moon, and we should use them to be to supply. So just like we did with Space Station, where we buy cargo services. We'll buy cargo services for this activity. It is a key piece of this architecture. It does not work with just NASA rockets alone. It has to be augmented heavily by the private sector and also international involvement.
So building off of that question, I guess what would you want to see more from the academic community? What can we as students do to get more involved? You know, classes like this, more studies, et cetera. Again,
I think, you know, like this study you just completed, which is really, really, really good. It can help us with some of these things. Are these concepts right? What is it like staging out of the vicinity of the moon? Is that a good place to stage? What is the specific orbit? What do the return options look like from Mars? You know, help us with what is the right sizing for some of these propulsion systems, and what is the right load? What is the right habitation? Where are the big levers? So treat these things as a problem of variables, and then, you know, trade things back and forth and help us understand where the coefficients are that drive certain aspects, so then we can focus design areas in that. So this needs to be done with a rich environment, and the key thing is it's not a debate about the one perfect architecture. We're trying to create an architecture that's resilient and can evolve. And so then if there's somebody comes up with a new idea, it isn't the end of the whole world. We're going to go ahead and inject that new idea. So I'm very interested in new ideas coming from academia, new studies, new ways of doing business. How do you take these basic components and use them in a new creative way to do something that maybe we didn't anticipate? And you noticed I called you on the second chart, I said that was a reference planning. That's our concept. You know, we chose to do the deep space transport as one piece because we wanted to minimize the weight. I didn't want to have modules and hatches and other pieces to have a very heavy spacecraft. That was done purposely. Is that the right thing to go do? On the deep space transport, or excuse me, the Deep Space Gateway, we could have launched all that in one single flight. I chose to launch that in 3 flights because I don't have the funding up front to build that in one monolithic piece. So there's a funding political consideration that sits behind these charts as well as a technical engineering piece that sits in these charts. So you can help me with the technical engineering piece, then I can explain to you the secret decoder ring of what's going on from the political other side behind the teams, and then we don't have to debate about what we're doing. We can see how we're trying to do this objective together.
To answer that, there's a lot that we as students don't know what is going on. Like you say, you know, the secret in the background.
Yep.
Are there channels that we can find out more through? And if not, then how can we improve those channels?
Yeah, we try to do a lot of stuff in social media. We try to do a lot of stuff on the web. I'm here today talking to you about these charts specifically for this reason, to get your input. We're trying to get this out as strong and as hard as we can. If there's things that you can't find easily, you should talk to your professors and let us know, and maybe there's another channel we're not aware of that we should be using to get information to you that you can use. Because we do a lot of social media stuff now. We do a lot of stuff out on the web. It should be out there, but it's not always easy to find where it is on the web. But all this stuff is open source. It's all out there. All our design stuff is out there. It's available, and you can go grab it. It's obvious from the studies that the students have been using a lot of our papers, a lot of our research. So there's obviously some of it's getting out there, but we can do a better job and get more. All right, maybe one more question, and we'll call it a day. Or maybe no more.
So to kind of build on that last concept then, if you have commercial people and students helping you, what can the average American citizen do?
The same kind of thing. I mean, I think there's great ideas from the public. We do. I'm continually surprised by things that I would say the public in general, non-professionals, can actually contribute. We did a science fair activity where a student in Egypt wanted to understand how a jumping spider would capture food in space. And I thought, this is not so good, but then it was really intriguing to see what that really spawned. The spider learned to actually walk and crawl across a screen and grab fruit flies instead of jumping. And then it got returned on SpaceX, which was amazing. It was the first animal to be returned on SpaceX. And it went terrestrially, and it tried to do the same thing. It tried to walk, and then it immediately started jumping. So it's kind of neat when I see students and the public in general ask questions that, because we're in the business, oh, that's a stupid question, we wouldn't even ask that question. They're uninhibited by that fear of being wrong or being embarrassed by asking a dumb question. They ask questions that if we as professionals and you as students take in seriously, there may be a piece of that question that may actually spawn a new initiative and a new way of doing business that actually outperforms anything we would have done in our linear fashion of just kind of working through the process methodically. So I think we need to all be open to the lay professional and not discount what the lay professional can do. It's amazing what you can do with a computer today. A lot of folks can do orbit analysis, they can do structural analysis, they can do virtual reality that in the past, those had to be done by a professional organization. They can now be done by essentially citizens at home. And 3D printing is another thing that's absolutely amazing. You know, we were asked about 3D printing. We printed a 3D X-band antenna on board Space Station the other day. And so that's the first time and we're going to coat it on the ground. We haven't figured out yet how to coat it, but we printed essentially a piece of a spacecraft. When Kate Rubins was on board Space Station, she wanted a centrifuge. So we printed her a plastic disc to which she could insert the test tubes in. We gave her the drill, put the drill on there, and she made a centrifuge out of a drill and a printed disc and the test tubes, and she centrifuged all her biological samples on board Space Station with no hardware from the ground. That came about from some just creative folks thinking about ways to use things in a new way. So I think we need to use everybody. As you saw with the students' presentation, this is an immense challenge. This doesn't come from any one of us. This requires all of us as a planet working together. This takes the best and brightest. This is what makes humanity great. This is the kind of challenge we need for humanity. So again, thank you very much.